Yes.
Okay, great. Okay, so on the agenda today is, I guess we're going to go through the lesson 3 as best we can. It's a really long lesson. And then after that, we have, I believe someone is presenting a nice paper.
Yes, it's me.
Okay, great. Is that Rob? Which one is presenting the paper?
That's Philip and Rob probably also. I don't know.
Oh, okay, so there will be two.
Schedule.
Okay, so there will be 2 presentations?
No, I'm not planning on presenting anything.
Okay.
I can talk about image augmentations.
Oh, that's right. Okay. Okay, well, okay, so let's do that as our agenda, just going through the lesson 3, and then having Phil make his presentation, and then having Sonia make his presentation on augmentation. Does that sound good?
Sounds good.
Okay. Are there any other items that that I'm missing that we wanted to include in the meeting? Okay. Okay. Well, so what I did was I ran through. There are 4 notebooks in lesson 3. He's basically giving you a whole overview of the entire rest of the course, and then he's going to come back and talk more about each one, I think. So the first notebook is a multi-class classification problem using the planet, using satellite images of the Earth's surface. And in those images, we want to classify things like haze, vegetation, bare ground, and so on. There's several different classes. This is maybe unfamiliar because well, from lesson 1, we did things like classifying dogs and cats and so on, and things that are either one class or the other. But this data set is new. It's a new experience because, let me see. I hear some birds in the background. I don't know how to mute everybody, but I want to do that. Is there a way to mute everyone and then see? Yeah. Okay.
I think if you click on the participants tab, and there might be a button to mute also.
Oh, participants tab. Okay. I just click that and manage. I see manage participants. So I don't know how to mute. Okay. Well, anyway, we'll just have to live with the birds in the background. Yeah. So I'm going to go to this. To this multi-label prediction data set. I'm going to share it. I'm just going to share the notebook now. Can everyone see that? Can everyone see what I'm sharing, which is the
yes, I can see it. Yes.
Multi-label prediction, right? Yeah. So what makes this different than the first classification problem we did is that in this problem, each image is going to belong to possibly belongs to more than one class. So for each image, you might have one class. It might belong to one class, or 2 classes, or 3 classes. So there will be multiple labels for each image. That's what makes it different from the ordinary classification problems that we did in lesson 1 and 2. So I guess I actually ran through this. But it's not practical to run it in real time because some of the training takes a long time. But he does a lot of interesting things here that you'll be doing again and again. One is he gets the data from Kaggle, and to do that he installs this Kaggle API so that you can get into Kaggle and actually download data sets from them. So you install that. You then make a directory where you're going to keep your key because Kaggle gives you an API key that you need in order to proceed. And so the first thing you have to do is you have to make a little directory to receive that. Hello, can people mute themselves because there's a lot of background noise? Hello? Unless you need to say something. Yeah? Thank you. All right, so first you make this little directory .kaggle, then you download from the Kaggle website for this competition. I'll just open that and show you what that looks like. You go to the Kaggle website, you get yourself an account if you don't already have one. I guess it's slow. I'm going to go back. That's not good. Anyway, I'm not going to go there. So you download the API to your machine, and then you upload it to your space. I'm in Paperspace right now, but you might be on your own machine, or you might be in Colab or somewhere else. You need to upload that little API file, which is called I think it's called Kaggle.json. So you make the directory to receive it, then you move it there to that directory. Well, first you upload it to your working space, then you move it into that directory, and then you're all set to download the data. So the next few steps are downloading the data set, unzipping them, and then there's a little thing here. It warns you that your Kaggle.json file is readable by other people, so you got to do that. If you want to secure it, you can do this. You do this little chmod 600 on it, and that makes it private to you. Right. Then you need to unzip these things, and so you have to install 7-zip. And so they've made a really nice little notebook here that has all the commands to do all this stuff. So unpacking the data, reading the training data, then he sets up the transforms. He's got this interface called the image data, the data bunch image, the data bunch API in Fast.ai. And the procedure, the interesting thing is, for all these 4 notebooks, the procedure is sort of roughly the same. You first get the data, then you split it into training and validation sets. Then you then you do whatever pre-processing you have to do on it, like transform it and so on, normalize it, and then you grab some data and put it into you grab the data and put it into a mini batch and load the mini batch onto the GPU, and then you start training. So he goes through this where you and in this he's using this for this image data set. He's using the ResNet 34 or the ResNet 50 model, and basically then he, once you create the mini batches and you're ready to train, and
one can come on.
Yeah. Hello?
Come on.
Comment?
You don't know that.
Hello? Oh, okay. Okay, so anyway, that gets to the end. That he trains this thing, and he gets, and then at the end, there's a section of which he talks about later, where you can actually submit this to the leaderboard in Kaggle, and find out what your score might be.
I really don't understand.
Okay, excuse me, can people mute themselves unless they have a question or a comment?
You can mute everyone. I think.
How do you do that? I know, I wish I could, but I don't know how to do it.
Joseph, you need to master mute everyone. You're the moderator.
Okay, right. So I go
an option to do that.
I go to manage participants where I'm like, oh, there it is, mute all. I can do that.
Some people appreciate this.
I'm going to mute everybody. Thank you. And then I'm going to unmute myself. Let's see. Okay.
We can hear you now. It's great.
Okay, excellent. Okay, so I could go through each of the remaining notebooks, but I think maybe a better thing to do would be to go through the notes that Hiromi took and just kind of highlight some of the things that she did. So I'm now sharing. Let's see. Here we go. I'm now sharing the notes that Hiromi took. They're linked to on the from the Fast.ai website. And she made some great notes on lesson 3 where she actually went through and highlighted major portions of what's going on in the video. And well, let's see. At the first part of the video, they talk about this ZEIT thing, which allows you to serve your models once you've made it. You can serve it online in an easy way. I haven't explored that yet, but I certainly want to soon. Then she highlights some of the nice examples that people have built. One of them by Christian Werner, who's in our group sometimes, and there look like some really interesting ones that I haven't checked out yet, especially this time series one by Ignacio. But anyway, these are worth checking out, I think. All right, so this is the multi-class data set that we just talked about, and here's what I mean by the multiple labeling. Each image has several labels on it. Partly cloudy, cloudy, agriculture, road, all of those kind of things. Each image can have more than one label. All right, so she goes through downloading the data, which we did that, and then here's the one of the things you have to do is to get the labels of the from your training set, and the labels are sometimes stored. Sometimes they're actually stored in the file names, or sometimes they're part of the file. So there's various ways that you have to figure out how to get at those labels, and I think the interface that Jeremy's built has various methods of getting at those labels. Okay, so
Hi, I've got a question, if I may.
Yes, sir.
Do you get a feel for how small a feature needs to be before it's registered?
On these satellite images.
Yeah. So if it's like a small patch of land, how is it? 20% of the size of the image, or?
That's a really great question. I mean, I think if you look at, I haven't studied that myself, but if you look at some of these images, you can sort of see, like this one has agriculture, and you see this patch is fairly small, and road, that would be a road. So that, so it's looking at things on that level. And I think to get a better feeling for this, you should just look at a lot of these images.
Yeah, I'll try it out. I'll give it a go.
Yeah, that's a good question. So it's basically lesson 3 is getting familiar with this new API that they've built that they're so proud of. Going through the steps of loading the data, splitting it out into training and validation sets, then and then putting it into mini batches. First transforming the data, whatever transforms you have to do, like maybe image augmentation or whatever, then forming the batches, the mini batches, and then training, and then getting your results. So he goes through all those steps, and let's see. The last step is this data loader step, where you create these mini batches, and you grab your examples from your training set. Create a batch, whatever the batch size you wanted, and then the step you have to put it on the GPU into the GPU memory, and then you do your training. So that's this class data bunch. You create these data bunches, and whether it's images or text, it's a similar process. They just have different different commands that are within this API. So let's see. So the name of the API is called Data Block, I guess. And now I don't remember him talking about the MNIST data set, but maybe he did a little bit as a diversion. But that's also a classification data set. But in that case, the classes, there's only one class per image. So that's going back to the kind of stuff we did last time. Okay, back to the planet data set. Here's another thing that answers this gentleman's question. Michael's question. Here's a small cloud, and that was enough to make the label partly cloudy, and so on.
Yeah, that's great. Thank you.
Yeah. Okay. So the next data set they do is this CAM-BID data set, where this is a new kind of classification problem, where every pixel in the image is classified as one of a number of classes. And in this case, I think there are like 32 different classes in this array here. And the classes are building, bridge, road shoulder, road train. This is obviously connected with the autonomous driving effort that's going on all over the world. Okay, so this is what the images look like when they're all labeled. And Jeremy points out that it's really tough to get an example of a labeled image, because you can see how much work it is to do all that labeling. Every pixel has a different color corresponding to what its label is. So each pixel in this case is a member of one of the classes. It's either a building or a road or a car or whatever. So here's some examples of images that are labeled that way. And it's called the CamVid dataset. There's another dataset called COCO, and he talks briefly about that, where you label objects in the data. That's a little bit different. Object detection data. So in that case, and I think he's going to come back around in this class to other problems with this. But this is the general class of object detection, and the goal is to draw a box, a bounding box around, find objects and draw a bounding box around them, and then inside that box is a label, whatever that image is. And again, it's a multi-class problem because each image can have more than one items in it. So here's an image that has number of chairs in it or whatever. This image has only one thing, a vase, that sort of thing. So he doesn't do too much with the COCO data set. Let's see. Now he circles back onto creating a data bunch from the satellite data set. He goes through that. Talks a little bit about image transformations, warping the images, and warping is to change perspective. And I think, like, he talks about if you're taking a picture of a cat or a dog, it's important whether you're looking from above or from the side or from the front, and what angle you're looking at. But when you're looking down on satellite imagery, that's not so important. You don't have to really worry about that. So the data augmentation that's important for satellite imagery is flipping the image vertically or horizontally, or I don't know what else they do. You could blur it. I'm not sure what they do as far as the transforms are. So okay. So then he goes to using ResNet 50 to create this multi-label classifier. And he talks about this new kind of accuracy metric that you're going to need. In order to decide what class something is, you generally have to use a threshold. And if your output probability is greater than some threshold, then you classify it as that class. So you can imagine for this classifier, it's going to have an output for each of these 32 different classes: building, car, road, whatever. And the output of the neural net is going to give you a probability of whether it's whether it should be labeled as a road or whatever, or a cloudy patch or whatever. And so you have to decide what your threshold is. If you're happy labeling something as a road, if the threshold is 20% or something, or is 0.2, then that's what you set your threshold. So that's something that you have to set by playing with it. And I think that that Jeremy has set the threshold to be 0.2 from his experience. So that means that if anything has a probability, a class probability of greater than 0.2, then they actually label it with that class. Does that make sense? Okay. All right, so he mentions how he used ResNet 34 first, and then he used ResNet 50, and it got better results. He goes through several cycles of training, and he ends up with a pretty, it looks like a really accurate result. Here's all the classes again, or there's 17, I guess. Maybe he used a subset of the classes. Anyway, so there's 17 different classes. You get one probability for each class, and you pick the classes that for which the probability exceeds the threshold. So on some pictures you might not have any classes that exceed the threshold. In that case, I think you just label it primary or something. I think primary. Anyway, so he says 0.2 is the threshold that he uses. And he talks about this function, this Python function partial, which is kind of interesting. It takes as input a function on the first as its first input argument, and the second input argument it takes the value, the input value of that function that you want to pass to it. So this accuracy threshold function, which he defines above, has an input of thresh, and this command is how you this partial command is how you pass a threshold of 0.2 into that accuracy threshold function. It's a new function. It's a function that I didn't know about in Python. But anyway, it looks like really useful. Then he talks about the I think he talks about the the F score, which is what Kaggle uses. And the F score is kind of like a combination of accuracy and false alarm. Well, I think they talk about precision and recall are the terms that they use in machine learning. Recall is the fraction of correct detections that you make. And precision tells like how accurate are you when you say something is a road, what fraction of the time are you correct? So like, because like there could be a lot of false alarms. So the precision is, let's say is like the number of times you said something, the number of times something was a road was actually a road divided by the number of times you said it was a road. So if you're giving a lot of false alarms, and then the precision could be small. But if every time you said something was a road, it really was a road, then your precision would be 1, and that's what you're aiming for. So there's these two measures, recall and precision, and the F score combines them both. And I think it uses a harmonic mean or something, but it combines them both into one number. And that's what this F score is. And they use for the one that they use in Kaggle, it's called the F2 score. And he talks a little bit about that. So, okay. So this is what you're learning. We've seen this in the last lesson where a typical learning curve where you start increasing the learning rate and watching the loss go down. And then even after the loss reaches its minimum, you continue to ramp up you continue to increase the learning rate until the loss goes crazy, and then you stop, and then you back up, look at this thing, and decide where to set your learning rate. And usually he says to either back off an order of magnitude from the minimum, or somehow find or just eyeball where's the steepest slope. In this case, it's about the same. Anyway, so for this thing, they set the learning rate to be 10 to the minus 1 first. So he said, find the thing with the steepest slope somewhere around 10 to the minus 2. Yeah, 10 to the minus 2 is right about here. That's where the steepest slope is. So that's where you then set the learning rate, and then you do it for a few cycles. And that's what he said here. And he says that they get this great accuracy of 96% and a F score of 0.92. So that sounds pretty good. And all right, talking about, then he talks about unfreezing. Now you have this ResNet, and it has all these pre-trained weights. And so now he's going to say, okay, let's unfreeze. And I think what that does is it allows you to tune all of the earlier layers that you didn't touch before. Just tune them a little bit. And so here, again, one of these learn recorders, you find that the learning rate takes off, or the loss takes off after, say, 10 to the minus 4. So now he's saying, okay, let's make this sort of two different, let's see, he specifies the slice, which is a lower limit and an upper limit of the learning rates. And the lower limit is 10 to the minus 5, and the upper limit is LR over 5, which is, we said LR was 10 to the minus 2. So it's going to be within this region, something like from here to here. And you're going to sort of ramp up the learning rate from the earlier layers. You're going to use the low version, the low values, and then you're going to start increasing the learning rate as you go towards the later layers, because the earlier layers are probably well trained. You don't want to mess with them too much. And so he's doing the training again, and he's continuing to improve. And now we see for the first time here that the training loss goes below the validation loss. So now you know you're not underfitting anymore. All the time here, the training loss is higher than the validation loss. And that tells you that you're underfitting. So you need to train more. Now here, that's why he already knew that he only needed to do 5 epochs, because at the 5th epoch, you notice that the training loss is now slightly lower than the validation loss. And now you're sort of in the territory you want to be in. You're sort of where they're close together, but the training loss is a little bit less. The training loss should be less because you know, you've actually used that data in the training, and the validation, you haven't used that in your model. So it stands to reason that it should be a little worse. All right. he talks about this data block this data block API a little bit here. We all need to read more about that. Let's see. He talks a little bit about how you choose the learning rate before you unfreeze, and we mentioned that you don't choose the bottom, you choose the steepest slope. So that's right around 10 to the minus. That's why they chose around 10 to the minus 2, and so on. Okay. He talks about improving. He talks about this thing called progressive resizing. So the first time he goes through these images, he uses 128 by 128. He compresses the image to 128 by 128, or downsamples them, and trains on that. And then when he gets that going, when he gets a good model, which we've gotten to here, when I showed you here, the model is now pretty good. Then he circles back around and says, okay, now let's take the same model and train on the full-size images. And he's said that people have discovered that that's a really good method of training to do even, to get your losses down even further than you did in your first pass. All right, so he talks about that. He trains that model. I actually didn't get this far because it takes my machine ran out of memory and I had to restart it and everything. So I didn't actually get down to make this plot. But the very last thing after this is he shows you how to submit the model into the Kaggle competition and get a score. So that's kind of an interesting thing that I want to try. Anyway, back to the ChemVid. This is an example of the data from the ChemVid. So this is the raw image, and this is the labeled image, where each piece of the image is, each pixel in the image gets a label, and so and the label, and then so the pixels come in these bunches, like come in groups, clusters, and this is a person, a person, a person. This is a building, a road, and so on. These are road markings. Anyway, so that's the ChemVid data set, and he goes through training that. I won't go through all that. But at the end, he shows that, okay, so this is what happens. You do the data loader, you get your, you do your data bunch, so you have a batch, and then once you have a batch, it's nice to look at some of the things in the batch, so that's what he does here, show batch. You're looking at these labeled images. And then he trains, similar process to before. And let's see, I didn't actually finish this one. Actually, yeah, I didn't actually get to the end of this one because the final stages of training take longer. So I'm going to go back and do it again. But anyway, he did get a pretty good result with this. Then he segued to this UNet thing for segmentation problems. And I didn't really pay too much attention to this. He's going to come back over it later, I think, in the course. So let's just skip over this part. Oh, this is a nice video that somebody made of the training process. So these are these two dimensions are two of the weights, and this is the loss function, and it's showing how training is starting at a you randomly initialize the weights, and then by training with
sorry, Joseph, Marcello here. I have a question.
Yes, Marcello. Hi.
Yeah, actually, it is on the previous part, not on these pictures here.
Yeah.
One thing which is a little confusing to me about using the ResNet 34 for example, segmentation or image object detection is that I understood that the model we're using is sort of pre-trained with some image data set, and then actually we do a few epochs of training and then unfreeze and so on.
Yes.
So what is
the image
yeah. Well, I don't remember which is the name of the data set where ResNet is trained on.
I believe it's ImageNet.
Yeah, maybe it is. Probably it is ImageNet. Yeah, you're right.
Yeah.
But what is confusing me is that actually in the ImageNet, I understand is an image classification data set, and we are using it actually for different stuff like segmentation and other stuff. So I'm guessing is it's the same data set image. It's the same pre-trained model we are using for different purposes, like the segmentation and multi-class and so on and so forth. Or it's different. It's a different pre-trained model, and then if it's the case, I missed where is the difference, because apparently everything's so smooth, which is too good to be true to me. I don't understand.
Yeah, it does seem magic, but the fact is that these models, these ResNet 34, ResNet 50, are pre-trained models that use the ImageNet dataset, and that's it. These are the weights that were found in that original ImageNet dataset, and then we're taking those as a starting point, and then we're unfreezing we're training them little by little. First, you unfreeze just the last layer and train it for our problem, and then you unfreeze bit by bit the earlier layers.
I think the argument for this is that it's better than just using random weights instead. So the other option is you initialize with random weights, and having the pre-trained model is a better start by argument than having randomly initialized weights.
Yes, and the reason is that the ImageNet data set is sort of an archetypical data set, and all image data sets have things like edges and shades and so on, and so it's a very general concept, and that's what the earlier layers of these networks, these neural nets are learning. They're learning edges, shades, maybe parts of faces, or maybe, and you don't care. I mean, for our problem with satellite imagery, we certainly don't care about the parts of the ResNet that have pre-trained ResNet that have learned how to recognize eyes and dogs and cats and faces.
It's already good at recognizing daily life objects.
Yeah. So it's better than, basically what Sonny was saying is that it's a starting point. It's better than nothing, and then we train it for our particular problem here by unfreezing the weights and letting it train on the earlier layers as well. Does that make some sense?
Yeah, absolutely. Just to say that it's impressive that for so different applications, the same starting point is good as well. It is good anyway.
It almost seems like magic, and I think Jeremy is really excited because one of the contributions that he and his team made was to apply that same methodology to text data sets. So they took the Wikipedia data set as sort of their, and which has, I think it has like maybe even billions of words in it. And they took that and trained a language model on that. And so the language model recognizes things like sequences of words and so on. And so they use that to build a language model. And what a language model does is it takes an input of 1 or 2 or 3 or 4 words, or a number of words, a little phrase. A language model takes as its input a phrase and then produces what it thinks could come next. And it can put as many words as you want in that next line. So for example, you can do things like train on a database on Shakespeare's works, give it all of Shakespeare's text as an input, and then formulate some line, some phrase, and give it that phrase, and then it will produce an output that what it thinks how Shakespeare would have talked, or what that phrase would have been followed by in Shakespeare's, if you were talking like Shakespeare. So that's kind of an interesting one of the applications. But in his case, he built this huge language model out of Wikipedia and trained it, and it takes days and days and days to train it. And so now you can benefit from that by downloading his pre-trained model. And then that will be your starting point for any problem that you want to do, like, I don't know, say you're looking at movie recommendations. That's one of the things we're doing later, or medical records, or subsets of the English language that have their own peculiarities. But you start with this pre-trained language model that he created from the Wikipedia data set, and then you train it further for your own specific application. That's what we do later on the IMDb.
Yeah, that's clear. Yeah, the other thing which is impressive is that the same pre-trained model applies for different network architecture, because initially we started with the plain ResNet, and then it is the UNet for the segmentation. So that's
I agree with you. That gives pause, and I would like to think about that some more, because you're right. I mean, we're doing different things. We're classifying individual pixels, and it's hard to see how, you know, all the knowledge that you learned from classifying images applies there, but apparently it does.
I think the magic is also there in the ImageNet dataset. So this dataset, come to think of it, has so many images and classes in it that has also sort of helped the community. And
Yeah,
that is
I think
also,
it's 1,000 something classes, or is that right?
yeah, 1,000 classes. And I think that's also why NLP is sort of behind that. We do not have a ImageNet like dataset for NLP right now.
An ImageNet data set for what?
NLP for natural language. So I suppose that's another reason natural language is sort of behind image.
Yeah, and this is what Jeremy's group has done for them. They've produced this sort of ImageNet-like database, this Wikipedia database. I guess somebody else did that. Somebody else took well, I think Jeremy's group trained that their NLP, their language model, on the Wikipedia dataset. And that's kind of like the analogy to the ImageNet.
Yeah, it was a joint work with Sebastian Ruder and Jeremy.
Yeah, yeah. So apparently that's a huge contribution.
Yeah.
And yeah, so anyway, thanks for that comment, Marcelo, because
Okay, yeah, go ahead.
that's going to make me think too. Anyway, so this is kind of a really nice little video demonstration of how backpropagation, stochastic gradient descent works. So here's an example of, you know, this is your data, and then if you plot, that's your first guess, which is really bad. This blue line that goes like this, it's obviously the wrong slope, the wrong intercept. But using backpropagation, you actually get it doing this stochastic gradient descent, which is sort of exactly what's going on here. You get down to the minimum, you minimize the loss function, which is comparing the line that the data to your model, and you can see how it gets the model to be really well fitting to the data as you find the minimum in this space. Anyway, I thought that was kind of neat. Not sure what he's doing here. Oh, he's changing learning rates. Okay, so he shows how in some cases increasing the learning rate gets you down there faster, and that's what he's done here. Here you can see it gets down there right away, whereas here it takes a longer time when you're using a smaller learning rate, 0.1. So he shows how sometimes increasing the learning rate can speed up your training. But then he shows what happens when you use too high of a learning rate. Now he increases the learning rate to almost 1, and now you can't get there. It just keeps bouncing back and forth, and you never actually get a model. You can see the model never approaches the data. It just keeps bouncing around. So then let's see. Oh, well, he claims that he does get it, but I don't see it here. It says the point is that having too high of a learning rate means you're going to take much longer to get there. I don't actually see it getting there because I'm looking for a blue line that goes here, but I don't see one. Anyway, then he says if your learning rate is really too high, then you're going to diverge. Instead of going down, approaching the minimum, you're just going to diverge away from the minimum, and you never get there. So that's when you set the learning rate way too high. All right. What happens? I'll just go over this because I want to get to the next notebook. There's CamVid. Okay, so the next one is the head pose data set. This is a different kind of image problem. Here, instead of your output being a class or a discrete output, which is class 1, class 2, class 3, or class 4, or some combination of them, now your output is a continuous real valued pair of continuous numbers. Okay, and what you're doing is you're looking for faces in your image, and you want to find the geometric center of the face, which is this red dot here. So and so you start with this labeled data set where you get the coordinates of the center, and then your goal is to take new images and predict what the coordinates of the center of the face in the image is. So you see the output of your model is the x and the y coordinate of the center of the face. It's a continuous function. It's actually two continuous functions, not a discrete category. So it's a new kind of image classification problem. So he approaches it with this data, what do you call this, data loader or data bunch interface. It's approached exactly the same way as the other problems. It's just, there's just a few little wrinkles because this is a different kind of data. The first thing is you have this sort of array of magic numbers that comes in from your data set, from this rgb.cal file. So you need to read that in, and then that gets used in the subsequent pre-processing. So let's see. He's showing what the images look like. And this is a little function to calculate the center from the text. Actually, the center, you're not calculating it, you're actually getting it from the label, getting it from the label file or something. So apparently there's 3 numbers to worry about here that comes to the input, that comes into the input for generating the coordinates of the face. Okay, so he has this convert function that takes as inputs these coordinates and returns the x and y values of the centroid of the face. So he defines these things. This overall function get CTR, and it outputs the 2 numbers for the x and y coordinates on the. I'm not sure what these 3 numbers are that we're working with at first. These are sort of the raw numbers that come in from the labels, I guess. You're getting it from the input images, and you convert these 3 numbers eventually into the center coordinates. That's what this get CTR function does. So he starts applying. He shows you what that looks like for the first image, and then he creates this. Then he shows a batch of the images, what it looks like, and it looks to me like, yeah. I guess she points out that Hiromi points out that the red dots don't always seem to be in the middle. So they've got some kind of an algorithm to calculate the centroid of the face, and we don't really know what it is. But okay, so then you create your model and train it. And then the first thing you find is when you look at your results is that you're not quite, you're a little bit off. There seems to be some kind of a bias here, where here's what you predict, and here's where the real centroid is. So you're sort of too far to the right. And again here, it looks like you're a little too far to the right. And here it looks like you're too far up. Anyway, then he refined okay. So but it's still, it's still not bad. Okay. I actually had I ran this. I didn't get to the end of it, but I ran it, and I had some. Let's see, Cambid and Post. Yeah, because it looked like the first time the model was off, and then as you trained it, it got a little better. Let's see, that's what we just looked at. The last part of it, the last part of this little notebook is using data augmentation. So he defines this set of transforms, including lighting and warp and zoom and rotation and so on. And that should help you improve your model. But he just shows you how to do it, and it's up to you to try to retrain the model and see if you get better results. Anyway, so this is basically showing you how to do data augmentation if you want to do that. Okay, I'm going to go back to Romi's notes. The last one is the introduction to natural language processing, where he uses the IMDb, the Internet Movie Database. There it is. Yeah. This one takes a long time to train, so I didn't get through it. I just got through loading the data and the first couple of parts, but I didn't get through it. So I'll just go through what Hiromi says. All right, so the data comes in. You get three things. You get a negative or a positive. That's a thumbs up or thumbs down for this. In other words, the database is basically text reviews, and you have to decide. Your aim is to build a model that looks at a text review and decides whether it's a positive or a negative review. And so your training set consists of labeled data, text reviews, which could be many hundreds of words. They're just showing you the first few here. And then the third thing you get, so you get this label, you get the text of the review, and then you get this is valid, which is the Boolean, telling you whether it should be part of your validation set or not. So this way, you can build, this is sort of a direction for how to build your training and validation set. You just take, for your training set, you take all the rows that have is valid equal false, and for your validation set, you take all the rows that have is valid equals true. Okay. All right. So he goes through the process of what NLP modeling does. First thing you have to do is take the words and convert them into what they call tokens. And so he does things like, if you have a contraction like isn't, he splits that into two words, is and then n apostrophe t. And that's one of the things you do with tokens. You also have this token called unknown for words that are not recognizable. So if somebody misspelled something or you haven't seen that word before, a lot of times it'll just be misspelling. You just call it, you give it the token unknown. And there are other kinds of special tokens too, which I haven't looked into all of. But there's one XX, the XX defines these special tokens, XX unknown, XX pad. There's a bunch of others that I've seen too. And the second step is you convert all of the words into numbers, because that's what you need for machine learning models. They need numbers. So they have, that's what they call numericalization. And so that's this list of words converted into its numerical equivalence is compare, these two lines. Okay. So you do this tokenization and numericalization, and he has a data block. This data block API knows how to handle NLP problems, so it does a lot of this stuff automatically. So he has this simple command textlist.fromCSV. Text.csv, that's basically your input file. That's this huge CSV file with all the reviews in it and the labels and whether or not they're in the validation set. He's taking the column, he's reading in that CSV file, taking the text, that is the second column, just the review text. And then he does this split from df col equals 2. I guess that's the, not sure what that is. Label split from df. Oh yeah, this tells you how to split between validation and training. And the col equals 2 in Python, that means the third column, right? Because Python counts 0, 1, 2. So the label column is where it says yes or no, that's good or bad, that's for the 0 column. The 1 column is the actual text itself, and the 2 column is the that Boolean that tells you whether it's a part of the validation set or the test set. So using that column, using column 2 is how it tells it how to split the data set into training and validation set. All right, and then on top of that, you label using the column 0, which is the what do we call it? Positive or negative, the class positive or negative. So this is a really sort of a readable way. It's kind of like a clear way to see what they've done. And then once you've got the data split and labeled, you pass it to the data bunch and make a batch out of it. So this is called method chaining. This little, you write a command and then you do dot and then you write another command and then dot another command. It's like a whole pipeline. a little miniature pipeline that you can write in one line, and I think this is pretty cool. All right, so he creates the data set that way. Then he creates the, let's see, there's something about a data_LM that I haven't seen here. So he has this, instead of create CNN, you have this language model learner that he's created, that Jeremy's created, or the Fast.ai people have created. And it takes as an input one of these data sets. And I think she skipped a few steps because it also makes this data set called data_LM. I don't remember what's the difference between that and this one. As the pre-trained model, they take that Wikipedia language model that I told you about. Jeremy's group trained this model, and I think it took them days and days and days of GPU time to train it. And then this is something we'll learn about later. He does dropouts to help to stabilize the results so that it's not overfitting. We'll learn more about dropouts later on in the course, but this is just that dropout parameter that you need. So so here's an example again where we're using this pre-trained model just like you use the ResNet 50 in the image problem, right? It's completely analogous. Okay, Jeremy reminds us that when you use a pre-trained model, you have to use the same statistics from that model. And in the above examples, I didn't point it out, but they're actually, when they normalize the images and so on, they're using the normalization statistics that came directly from the ImageNet model, the pre-trained model that they used. Otherwise, it's cheating. You can't use the statistics of the data set that you're working with because that would be cheating. It wouldn't give you a generalizable result. And then, okay, so so he does a little bit with that. This is something he's going to come back to, building this recommendation system where you take as input a movie review and decide whether it's thumbs up or thumbs down. He's just giving an introduction here. He actually, but he actually has this. I'm going to go through this IMDb thing really quickly. Yeah, it takes a very long time to run this. I think hours, a couple of hours. So I've gotten down to the first part. But here, let's see. Should look at an example of a review. Yeah. So here's an example of, this is actually the second review in the data set. You can see that it consists of hundreds of words, and some of these words are probably misspelled. Actually, this one's actually pretty well written, so I don't see any misspelling. I don't see any spelling errors here. Anyway, so here's how oh, this is where he produces that data_LM that he used later on. So he produces a text data bunch from CSV from this text.csv file, which includes reviews like this. All right. Then he saves it. You want to save these things because if you run into an out of memory error, you have to, a lot of times you have to restart the kernel and then you lose everything. But if you have this saved, you can kind of restart everything at the point where you crashed out before, and it saves you a lot of time. Okay, so here's the tokenization, where he talks about the tokenization step again. And you can see that the original review is kind of garbled when you pass it through this tokenization step because so many words get replaced with different kinds of tokens. I'm not sure what this XXMAG means. But anyway, this is what it looks like when it's turned into tokens. And then you do the numericalization step where you convert the tokens into numbers. He's saying he has a maximum vocabulary size of 60,000. And so the numbers that you're converting the tokens to correspond to elements in this vocabulary. So, you know, if it says 41, if you convert some word to 41, to a number 41, that means it's the 41st entry in this vocabulary. So that's what he's doing in the numericalization step. Okay, so this is the tokenized data, and then this is the numericalized data. So I guess you can get at it by this dot data. You pull out the actual data that goes into the model is looked at by this dot data chained method here, and there are the numbers that correspond to the first 10 of the words in this review. Okay, talks about the data block API, the language model. He mentions you might need to change your batch size because it's GPU intensive. So I tried starting here, and then I noticed that there was one problem, and I still haven't fixed it. You need to have this this model, this LSTM model, and that comes from somewhere, and you have to import it. So I have to figure out how to get that. I haven't done that yet. But then I noticed that in his work below, it takes him 3 hours to train this one step, and he's working with a really good GPU. So the next steps in this, just kind of, you're going to need some time to get through them all. So I'm going to do that today, but I didn't have a chance to finish it before. Anyway, I'm going to, I think I've taken too long. I've gone through all of the stuff, and I'm really sorry. I should have watched the time. I didn't leave. I should have only taken 40 minutes at the most, and I'm very sorry. I'm going to stop the share and turn it over to Philip, who's going to give us an overview of the paper that he's been reading. So Philip, are you there?
Yes. Hi, I'm here. Can everybody hear me?
Yeah, we can hear you.
Test 1, 2, 3. Great.
Yeah.
Yep. Can hear you fine.
I probably should share my screen with you. I will try to do that. Can people see my screen now?
Yes.
Yes,
Yeah,
we can see
thank
the
you.
slides.
Yeah, we can see your screen.
Yeah.
Great. What I want to do today is I read the paper, Learning Independent Causal Mechanisms, and I have to tell you it was a little bit over my head. I actually wrote an email to Giambattista, one of the first authors, trying to clarifying it to me, but he answered, and it's probably all on me. So what I want to do instead now is I prepared a presentation about some thoughts I'd say, gathered recently. My research background is actually in causal inference. That's where I wrote my master thesis in, and I'm thinking for quite some time now about how deep learning plays into that. I will talk about this in this presentation. So I will give a full screen or change to full screen. Can people still see it?
Yep.
Yeah. Great. So the topic is deep learning versus causal analysis. It would actually be nice. First of all, I have to say hello to Charles, Joseph, Marcelo, whom I know from this meetup, and James Madden, I also know from the meetup. Unfortunately, the other people I don't know, but hello to you, to the guys, and of course, Sanya, hi. Okay, so it would be nice if you read the word causal analysis. Does anyone have any association with causal analysis, or is this unfamiliar territory, let's say?
This is totally unfamiliar territory, Phil.
Okay. Then I will allude to it a little bit. So this is a humbling starting thought by a British statistician called George Box, who said, all models are wrong, but some are useful. And this shall be our motto, not only in the meetups, but also in statistics in general. So what is causal inference? Well, it's basically the goal of all of science, whether it's epidemiology, medicine, economics, sociology, psychology. All empirical disciplines have at their core the goal of causal inference. The goal of science is not to predict well, which is sort of the aim of, as we will see, machine learning and deep learning, but to understand cause and effect. That is, understand counterfactuals. Counterfactuals is actually kind of a big word, but think of it like this. It's basically just the question, what would happen if? What would change if I would have gone to a different college? What would change, for example, in my earnings if I would have studied Y instead of X? How would the survival rate change if the patients were given a drug A instead of drug B? What would happen if we were to implement a law that prohibits smoking? Would we see an increase or a decrease in lung cancer rate? So as examples in medicine, there is the classical example of the randomized controlled trials. Think of it like this. A patient, like I just said, gets drug A instead of drug B, gets placebo compared to drug A, gets a gold standard therapy and a gold standard therapy plus some addendum drug that wants to show to be novel and better than the others. Then the example with health politics I just mentioned. Also think of economics or education, for example, that I already mentioned. Also, what is the causal effect of having a high school diploma or doing a training program or even going to college on later earnings? Now, the RCT is the gold standard. It is the gold standard in medicine and all of empirical disciplines, is to actually physically do a randomized controlled trials. So you randomize, you do a sample size calculation and you randomize patients. One group gets drug A, the other gets drug B. That is the only, I shouldn't say the only, but the best way or the gold standard to get a causal measurement or a causal effect on, let's say, for example, survival time. That way we can make sure that the drug is only dependent on the drug itself and not on what we call confounding covariates like age, sex, or whether the person is an athlete, for example. And here is a scheme or a diagram that shows it to you. You essentially flip a coin. That's actually a physical process. That's how they used to do it in the past. Now, of course, you can use a randomized computer algorithm that shows you a 1 or a 0, and the patient gets the drug or does not get the drug. Or in principle, you could also throw a fair dice and say 1 to 3. The patient gets the drug, and 4 to 6, the patient does not get the drug. But there's a problem. Although the randomized controlled trials are the gold standard, because of the aforementioned characteristics, they're not always possible or feasible. Think of high costs. They cost a lot of money. Only big pharmaceutical companies can actually perform a randomized controlled trials, or there might also be ethical concerns. For example, if we were to be interested in the effect of going to college on later earnings, or the effect on smoking on lung cancer rate. We might have observational data, though. That is actually nowadays we get huge amounts of data in electronic health records. These are data that are just, they're called observational data, and it's important to keep in mind that they are non-randomized. They're completely non-randomized. They're just descriptive data. So think about it when you go into a hospital, your blood pressure gets measured, it gets recorded if you're male or female, your height, your weight, and a lot of data gets measured. Now, there are statistical modeling techniques for causal models. For example, propensity score matching methods, structural equation modeling, or in economics, instrumental variable techniques, and in biostatistics, Mendelian randomization. And what I thought the paper was about, or should be about, how can we, or let's say, the AI in the future learn essentially cause and effect instead of just associations. And that's where we enter machine learning or deep learning. So we can define machine learning as an ensemble of learning algorithms that learn from massive amounts of data. Sorry for the buzzword, but I'm going to use it. I hope you understand that in this context, big data, okay? So deep learning is, we can define it as a subfield of machine learning where, of course, so-called deep neural nets, we have seen it with Charles last week, for example, are used that are loosely modeled on the human brain's anatomy and neurochemistry. And here we see a picture of a deep neural network. We have essentially input layers, we have hidden layers, in this case, 3 hidden layers and an output layer. And of course, there are weights between the layers, and these weights are then trained using the backpropagation algorithm. We've seen this with Joseph and Charles, and in all the past meetup episodes, essentially. And then the deep neural network learns something, namely it gets a high accuracy on picture classifications, for example. We will see that later. And the approach is always the same. As Joseph pointed out before, you essentially do a train test split. You train on a subset of your data, you train your model, and then you test it on your test set, and then you can get a measure of how correct you are, how good your model is, and whether you can deploy it in the real world or not, essentially. It's important, yeah, but that's always done to evaluate the model only on the unseen test data. Only that way you can get a an evaluation of your model, how good or not good it is. So this, we've seen impressive results in computer vision. We've seen this actually even today with Joseph's presentation. Let's think about this for a second. Facebook or Google have like 1 million pictures of bananas, and they train their giant deep neural nets on these pictures, and then they get an accuracy on a giant test set of 99.99%. And they say, okay, that's pretty cool, let's deploy it. And that's why we can now see in Facebook, okay, this is a banana, this is a stop sign, and this is a traffic sign, whatever you insert X here, your favorite application. By the way, every time you use a CAPTCHA where you as a human, and I guess we've all done that, say that this is a traffic sign or there's a car in the picture, you essentially provide training data to the tech companies. So this is image classification. So the algorithm or the system can sort of say this is a cat, yeah, and then on the right hand side we can see multi-object classification. We've seen that with Joseph today. This is nowadays also possible, and we've seen impressive results there. You can enter other application areas. We've talked about recidivism risk prediction recently, where models get deployed with, essentially prisoners, and they get a risk score on based on that they get, sorry, out of jail or not out of jail. This is, of course, a very high stakes application, and there are also ethical issues that we've talked about. Then you could think of credit payback predictions. So are you going to pay back your credit or not pay back your credit? There's also job performance prediction. There was recently an interesting case of a female teacher in the US that was fired based on a machine learning algorithm, and I think the last, I followed up on this case, and the last information that I have, she now went to jail with this case, and let's see how this goes out, because in principle, there should be some sort of explanation provided for her, because there were some metrics to be gained and so on, and she was actually a good teacher from what I've gathered. Also, customer demand prediction. This is more of a business application. All of that is quite impressive, and I'm perfectly willing to admit that, but we still don't get causal insights with that. And remember the beginning, that is essentially the goal of science and understanding the world around us. And this led to Judea Pearl, who is a famous causality researcher based at UCLA, saying or proclaiming rather provocatively that deep learning is just curve fitting. I thought about this real quick for a while because it's kind of, yeah. But then I figured, yeah, he's actually kind of right with this provocative statement. He later said, admittedly, these are very complex models in the case of deep neural nets, and we've seen that they require a lot of computational power and so on. But essentially what you're doing is you are fitting, or you're estimating weight parameters, essentially using massive amounts of data. So this brings me to the end. The take-home message for you, I guess there are many data scientists in the audience, so the thought for the rest of the weekend is that we as data scientists should be sort of more focused on the goal of science, and the goal of science must be to find cause and effect, not just associations. That's high predictive power in big data. Yeah, thank you. That was my presentation.
That was really fascinating. Thank you, Philip. I think I want to go off and try to read that paper now because causality is one of the most interesting things to me in all of deep learning, because and it's really a big deal now with all those European privacy rules and everything, where people are being pushed, or people who create these deep learning models are being pushed to be able to explain in any given case, why did your prediction do this? Like, why did you deny this person credit and you gave this person credit? You know, why did this person not get into this school? You know,
yeah, there are definitely some high stakes decisions being made on basically algorithms that we don't really understand. Yeah.
Yeah. So would you say that this paper is a good place to start, or maybe one should start at with a more introductory level paper? Or
I actually have it here. Like I said, I read the paper actually 3 times and then wrote to Giambattista, and he explained it to me. But I sort of my hope was that, or what I expected, it kind of like laying out, you know, like this is because they are over at the Max Planck Institute of in Stuttgart of Causal Inference of the Shirkoff group, and they're sort of famous for actually doing research on causality. And what I expected the paper to do is kind of like, okay, now we have trained these deep neural networks and so on, but we have actually managed to train them in such a way that they can actually predict, that they can actually get causal insights. And in the paper, it's actually mentioned there's a famous a framework in causality called structural equations, structural equation modeling, which a lot of social scientists use, where they can pre-specify sort of their theories. And their framework basically, they mentioned in the paper, should automatically sort of come up with sort of structural equation model structures, but I didn't get at all how that was achieved or in the paper. So in terms of general causality, I can recommend a book by the mentioned Judea Pearl. He actually wrote a nice book called Causality. Then I guess, yeah, also the classics, of course, Elements of Statistical Learning by Tibshirani, but that's more of like a statistical learning flavor, so not necessarily just focused on causality.
Judea Pearl has a more recent book, and it is a more general popular level. And this is what I've just started to read this book yesterday. It's called the Book of
Wow.
Why. Yeah, it's called the Book of Why.
Yeah, great.
Yeah. So this is sort of at a popular level. So it's written for at an ordinary people's level. So this doesn't, you know, it doesn't assume you're a technical person or whatever. And I think this is a good place to start. As you can see, I'm interested in this topic too. I like what you said, that his quote, what you said, that deep learning is nothing but curve fitting, because that ties in with something that Jeremy brought out in this video in lesson 3. I didn't go over it, but he talked about the universal approximation theorem, which where people say, and I think they've proven it, that any function can be approximated by deep neural networks.
Yeah.
No matter how nonlinear, no matter how nasty looking the function is, you can approximate it with an appropriate number of deep neural, appropriate number of neurons arranged in a network of the appropriate depth. So it's deep learning is curve fitting, and it's sort of a new way to think about curve fitting that I've never thought about. I've done curve fitting for most of my career, but I've never thought of it in terms of I never thought of neural networks as an instrument for doing curve fitting, but that's what they are. Okay, well, we still have 15 minutes for Sanyam. If you feel like you can do your presentation in the last 15 minutes, or if not, we can.
No, I'll try to complete it.
Okay.
I'll do one thing. I'll share the links in the chat as well for you to follow along.
Okay.
I hope everyone can see my screen okay now.
Yeah.
Yes, we can see.
Yeah, so there was a lot of chat going on in the chat section. There was some discussion about progressive resizing. So there was this Kaggle challenge, quick draw doodle recognition challenge. I had participated in this, and one interesting thing that we were able to find out is, so the main challenge with this competition was there were 50 million images to be trained upon. And to work on with the accuracy, what we did was we started out with 1% of the training data and 256 by 256 image size, went on to 5% with 128 by 128, 20% with 64 by 64, and the complete data set later on, and I think 64 by 64. And this was something that worked okay for us. I do not have extensive results of this because it was a big enough data set. It took 20 hours per epoch to run. But this was something interesting that we found out with this. So to my main presentation, I'll be giving examples of data augmentation using Fast.ai. In the previous presentation, I had taken a deep dive into how it's implemented inside of the library and where you can find the source code and all. This will more be of an example-based walkthrough where these augmentations might be useful. So first thing that I did was turn data augmentation completely off, and then for another example, I trained it for the similar number of epochs with everything on default. So all of the data augmentation set to be default. What I learned from this example was with everything off, it was slightly overfitting to the training data set, as you can see. So these are the values with everything, all of the data augmentations turned off. This is the Resonate 50 being trained. And same values for same number of epochs are slightly better with the default image transforms enabled. So to give you a proof by example that if you rely on the defaults and if you don't do any feature engineering or if you even don't pre-process your dataset, I'm getting a slightly better result as a proof by example. Next, I'll sort of highlight the augmentations that are supported by the library, including the fancy ones, fancy or exclusive, so to speak. So when you call get transforms, which is how you enable the default transforms inside of Fast.ai, you get these for free, or these are called by free. So what happens is do flips your image horizontally. Flip vertical is set to false. What that does is it flips your image along the vertical axis. Your maximum rotate and maximum zoom have some preset values, which I think Jeremiah said are based on intense experimentation. So I would sort of trust these okay. And if you look closely, it's a tuple that's been returned from the get transforms. It's of dimension 2. And the reason it's of dimension 2 is because these are for the training and the validation data set respectively. As you can see, for the validation data set, there's not a lot of going on. You just resize the image to whatever you set it to. For training data set, you have the defaults and everything that is enabled by by the library. Moving on to the example. So firstly, suppose these 19 image transforms and 3 convenience functions. What this means is when you're doing these either of or maybe all of these transforms, these convenience functions would be applied as an add-on. So you can randomly crop inside or out of your image. You can randomly crop into sections of your image. You can randomly pad your images. And as I'll demo, there are more options to randomly padding your images. And you can also randomly zoom in or into sections of your images. So for an example, these are the default transforms that you get for free when you call the get transforms function. You can notice that it's being horizontally flipped. The image is being horizontally flipped, and there's some amount of rotation and zooming happening. To resize, you can pass on size equal to whatever size you want. Rotation, how rotation works is you pass on the angle that you want to rotate it to, and what this does is it rotates between minus to plus angle values. So minus 180 to 180 degree. This wouldn't make sense with a dog image because I suppose no one would click this image in such funny angles. Where this might make sense is in a satellite image. So if you're looking for far away, to me, these might even look completely different examples. And I suppose this would be really helpful in such cases. The next transform is brightness. So brightness values vary from 0 to 1, 0.5 being the default, 0 being completely dark, 1 being the brightest. Based on my personal experience, this is pretty useful in OCR example. So when you're trying to extract text from images. And generally, you can never find the perfect image clicked by the client or inside of your data set. So you definitely need to play around with the brightness. And like from first looks, you can probably guess that at least to the human eye, 0.3, the text is pretty small. I apologize for that. So as you can see that this image would probably work best for the text extraction example. I suppose the best way to find out what values work best for brightness is through experimentation and maybe later going ahead and plotting what doesn't work for you by calling the interpret max loss or top losses function that is there in the library. For contrast, it's a similar scenario. You have 0 to 2, 2 being the maximum contrast range for the image. And repeating the same example, the same text extraction example, for you to be able to extract the text in its best form, you would want it to stand out the best from its background. So as you can see, for the highest contrast value, the text really stands out on this silver background. This is an image of a medicine. And what we want to do is extract whatever details are on there. So you would want to, again, set it to maximum contrast in such scenarios, maybe when the background is reflective or if the white background is a silver background. Moving on to cropping. What cropping does is cropping crops into and out of your images. Now, if you want to crop into a section of your image, if you're looking forward to extracting image, extracting the text from a particular section of your image, for example, you're working on number plate extraction and you know that for normal cars, the number plate will be in the bottom mid section of the image. You would want to pass on that value so that you can sort of focus your detector into that zone of the images. That's something you would want to keep in mind.
May I ask a question, Simon?
Sure.
Yeah, the picture you're showing right now with which appears to be text classification. So are you using that kind of picture for OCR, or it's just an example?
I've actually worked on this problem with the client. So this is from a project of mine.
Okay, because I understand if it makes sense to make this transformation instead of try to identify where the words, where the digits are, and then classify only the portion of the image wherever is the digit.
Yeah. I mean, I've also tried this with number plate recognition. So in that, you would want to focus it towards lower sections of the image.
Okay, thanks. You can go ahead.
So moving on to crop pad, what I'm slightly moving faster because we're short on time. What crop pad does is you have three options that you can set. One is crop pad with zeros. What zeros does is it puts around a black border around your image. So just 0 pixels. Another one is padding by reflection. What this does is around the borders, your image gets reflected. This might not be highly visible in this example because it's just silver that is being reflected, maybe in the size equal to 501. And this is the one that Jeremy highly recommends, and it's also the one that is set by default inside of the library. So I would trust to enable this whenever I'm working on a generic problem. This one is pretty interesting. Dihedron is a figure, and if you're familiar with it, it has 8 peculiar angles inside of it. So when you enable dihedral transforms, you get these rotations in 8 different angles. Again, if you notice, the reflection is set to, the padding is set to reflection mode. This might not make sense in the doggy image. So again, taking our satellite image example, and you can expect that the satellite might be looking at whatever objects you're looking at from the sky in all of these angles. So if you're working with, I would say, microbial data sets, microbial image data sets, or satellite imagery, you would want to enable the dihedral transforms. Now this one, I wasn't really sure where this might be very useful. Jitter, what this does is based on what magnitude you pass in. It adds random jitteriness or random noise to your data set. So from minus to the plus magnitude, and to me, both of the minus X and plus X images look pretty similar. Another cool transform or sort of exclusive transform to the Fast.ai library is perspective warp. And to give you the same example for comparison, it sort of warps around the image how it would appear in 2D as if the object had moved around. Based on my experience, again, if you're working on that OCR problem and you have the data set that has images clicked in weird angles, you would want to perspective warp it to an angle from where you can vertically read the text. So that's again something that might be useful. In this case, the images were perfect, so it doesn't make sense to perspective warp them. But if they're at an angle, you would want to warp them such that you can vertically, or your angle is set at 90 degrees above to read the data or text. Another, I would say, sort of exclusive transform is symmetric warp. To demo this to you, I would say if you're working on a object detector or a image search engine where you take, or the Google Lens, how this works is inside of Google Lens is, if you were trying to search up products from images, you would want to apply symmetric warp so that you get different angles of your product for free. You cannot expect everyone to set the camera to the perfect angle when they're searching for a product. So this might be useful in that case. Tilt is pretty similar to it, and repeating the same example for it, you can specify the direction and if you want to move it in forward or backwards. So again, if you're working on a image search engine and you want to make sure that your model can recognize all angles, you would want to work with this transform enabled in your training by default. Cutout, what this does is, and I'm sorry, you don't have an example for this. What this does is it cuts out sections of your image. Again, I'm not particularly sure of where this might or might not be useful, but again, this is one transform that is supported by Fast.ai. And I've been able to just finish in time. I leave it open for any questions that might be there.
Stanley, could I ask a question?
Sure.
If you ticked all the options on the augmentation, so you turned everything on, how would this work? So you'd be going through your epochs, your mini batches, and surely you wouldn't apply every single augmentation to every image in the mini batch, or would it just be a random selection?
So there's something called probability affine. Whatever value you set it to, these transforms are applied with that probability to the mini batch.
Right.
And you wouldn't want to enable everything because it might just blow your model off the rails. For example, dihedral transforms might not work well with every data set, so on and so forth.
So Sanyam, does this mean that for every image, it calculates this affine probability for applying transforms for each of the different transforms, and then
That's right.
if for a given image that it could draw more than one transform to apply, although it's probably highly unlikely that it would draw all the transforms, but it seems like
That's right.
it could draw more than one transform to apply.
Yes, that's right.
Okay.
So this will put up your processing time greatly, won't it? If you turn a few on.
I suppose this happens on the fly, and I haven't seen any differences, and I would trust the Fast.ai library to be able to work on this in real time. So I wouldn't say this would bottleneck anything.
Do you think that this would be a process they would use the CPU for, or for the GPU, or the GPU for?
I'm not sure, but I think CPU cores.
I think CPU. Yeah.
Mm-hmm.
Any other questions related to image augmentations?
Can you talk a little bit about the use case for, you're showing some things of the tablets. How exactly did you use that? What was the project about?
So we were working with the client to pull out the details on the tablets. And the issue with that is, especially with these silver background images, there's a lot of reflection happening on, and you want the text to stand out or be at maximum contrast on the background. So one thing you can do is just crop into wherever the region of interest is. Another one is you can increase or decrease the contrast, and we did not use Fast.ai for this, so we were just manually triggering it with OpenCV library. And another thing you can do is you can play around with the brightness values to increase or decrease them to an extent so that it works best to be able to extract the images.
I suppose that for this problem, you might be able to do some kind of object detection. So draw a box around the part of the image that has the labeling in it, and then just crop the image down to that part. That's probably it.
The issue with this particular project was that the images had a lot of reflection and extra lightning going on.
I see. But still might be possible to train a model to recognize when there's that crosshatched reflective background versus the background that has text in it. And then you could have an object recognition step where you just crop out the part of the image that has the text in it and then go forward with that.
In theory, yes, but I suppose that would require us to annotate the data. So that was something that I wasn't excited about.
I see. Yeah. That's exactly. That's theoretical, and it probably takes a hell of a lot of work to do it.
But if you tile the image and just step through all the tiles, and you pitch your tile size roughly the same size of a letter, couldn't you use the dogs and cats sort of, not dogs and cats, the dog breed sort of classification technique on each one?
So for this particular image is sort of the best image that I could pull out of the data set. All of the others are pretty much at funny angles, or either overexposed or too underexposed. Yeah,
but a bee is going to be a bit like the MNIST, isn't it? It's always going to be a bit of a bee.
Yeah.
But if you tile the image, according to some scheme, you might get only part of the bee, in your tile.
I didn't consider that.
If you're trained up on lots of parts of bees' whole and bits of bees, then I'm sure you'd get a pretty good picture of what's a bee.
Yeah, I did not give that thought, but I'll try experimenting with that.
Anyway, that was really interesting. Thanks.
Okay, well, I want to thank Sanyam and Philip for their excellent presentations. This is really great, and the fact that you were able to do it in the small amount of time that I left to you, really appreciate that.
No problem.
So, any other thoughts? I guess we'll have to take this offline to figure out what to do for the next meeting, but we are going to go through lesson 4, and I'm not sure yet who. Somebody had volunteered to do it, I think, and then we'll go to the Slack channel to figure out who wants to do presentations, and we'll organize it that way.
For next week, I am presenting, so I'll take up the lesson. If anyone wants to present anything else, they welcome.
Super. Okay, we'll take it up on the Slack channel. Okay, everyone, thank you for being here, and we'll see you next week.
Thank you.
Thanks, everyone.
Bye-bye.
Bye.
Bye.